Well, in this lecture, we will prove a theorem that will help us in obtaining the characteristic polynomial of a linear operator T in terms of its restrictions on the T invariant subspaces. But before doing that theorem, we will do an exercise that will help us in proving the theorem. So let's start with this exercise. Suppose T is a linear operator. Let T be a linear operator on a finite dimensional vector space. On a finite dimensional vector space V, such that V is equal to the direct sum of its two subspaces W1 and W2, which are where both W1 and W2 are T invariant. Now, if TW1 and TW2 denote the restrictions of T from V to W1 and W2 respectively. And this is the matrix of the linear operator T with respect to some basis beta. B1 is the matrix of the linear operator T W1 with respect to the basis beta 1. This B2 is the matrix of the linear operator T W2 with respect to basis beta 2, where beta is equal to beta 1 union beta 2. Then this matrix A, this can be partitioned in this way. We have the block diagonal partition of this matrix. Here we have B1, then 0, then 0, and B2, where B1 is a matrix of order equal to the dimension of the vector space W1. Beta 2 here has its order equal to the dimension of the subspace W2, and the 0 and 0, they are the matrices of some appropriate sizes. Now let's solve this exercise. So solution. Now we are given that this beta 1 is in fact a base of W1, beta 2 is a base of W2. So let beta 1 be the base of W1, which is equal to V1, V2, so on, Vk. So that is, we are assuming that the dimension of W1 is equal to K, and we are given that V is a finite dimensional vector space. Similarly, let beta 2 be equal to Vk plus 1, Vk plus 2, so on up to Vn. Then we write beta is equal to V1, V2, Vk, then Vk plus 1, so on up to Vn. So let these be the standard, be the ordered basis. Let these be the ordered basis for V, W1, and W2 respectively. So we choose these to be the ordered base of W1. This is the ordered base of W2, and similarly we define beta as the union of these two bases in this way and call it as an ordered basis for the vector space W, and this union is the basis for W. It comes from the fact that V is a direct sum of these two subspaces. So therefore the union of the base of W1 and base of W2 will give us the basis for this vector space V. Now first we recall how we have to define the matrices A, B1 and B2. Now the matrix A, which is the matrix of the linear operator T relative to the basis beta. Now we know that its columns are defined in this way. The first column is the coordinate vector of V1 relative to the basis beta. The second column is the coordinate vector of V2 relative to the basis beta, and so on. And similarly, the last column is the coordinate vector of Vn relative to the basis beta. So this is how we define the columns of the matrix A. Similarly, matrix B1, it is the matrix of the linear operator TW1 relative to the basis beta 1. So its columns are divided in this way. The first column is the image coordinate vector of V1 relative to the basis beta 1, and so on. And similarly, the last column is the coordinate vector of Vk relative to the basis beta 1. So in fact, we can see that this is an n cross n matrix. This is a k cross k matrix. And similarly, B2, which is the matrix of the linear operator TW2 relative to the basis beta 2. So its columns can also be defined in this way. It is TW2 of Vk plus 1 relative to the basis beta 2. Then similar the second column and third column, and similarly the last column is TW2 of Vn relative to the basis beta 2. And in fact, this is a matrix of order n minus k cross n minus k. Now we will first evaluate one by one what are these coordinate vectors. So now, since this TW1 and TW2 are the restrictions of T from V to W1 and W2. So we have this T of Vi is equal to TW1 of Vi, where I runs from 1 to k. So if this Vi is an element from the basis beta 1, then we have T of Vi is equal to TW1 of Vi, and this comes from the definition of the restriction of the linear operator TW1 from the linear operator T. And similarly, we have T Vj. This is equal to TW2 of Vj, where this k plus 1 is less or equal to j and less or equal to n. So in fact, for the image of Vj from k plus 1 to n, T of Vj is equal to the TW2 of Vj, and this also comes from the definition of the restriction TW2 from the linear operator T. Now we will use these two factors to evaluate these three matrices. So now we will do them one by one. So now this T W1 of V1 related to the basis beta 1, which is in fact the first column of the matrix B1. Now, since TW1 is a linear operator from W1 to W1, which is because this W1 is a T invariant subspace. So therefore, TW1 will be a mapping from W1 into W1. Now, since this V1 is an element of W1, so therefore TW1 of V1 is an element of W1. So therefore, we can write it in the linear combination basis beta 1. So we write TW1 of V1. This is equal to A11 V1 plus A21 V2 plus so on plus A K1 Vk. Because we can see that V1, V2, Vk, they are the K vectors from the basis beta 1. But now this can also be written as A11 V1 plus A21 V2 plus so on plus A K1 Vk, then plus 0 times Vk plus 1 plus so on, and similarly 0 times Vn. But now this is actually the coordinate. This is the representation of this TW1 of V1 in the basis beta. So therefore this in fact equal to T of V1 relative to the basis beta. Now similarly, T W1 of V2 relative to the basis beta 1. This can similarly be written as A12 V1 plus A22 V2 plus so on plus A K2 Vk. But now this can also be written, it is equal to A12 V1 plus so on plus A K2 Vk plus 0 times Vk plus 1, then 0 times Vk plus 2, and so on 0 times Vn, which is in fact T of V2 related to the basis beta. So therefore in this way we can continue and we can write T W1 of Vk. So this is T W1 of Vk. We can find it is coordinate vector related to the basis beta 1, and this is equal to A 1k V1 plus A 2k V2 plus so on plus A kk Vk. But now we can also write it, it is equal to A1k V1 plus so on plus A kk Vk plus 0 Vk plus 1 and so on 0 Vn. And this is also equal to T of Vk relative to the basis beta. So therefore, in fact, this first equation will give us the first column of the matrix B1. But now this representation, which is T V1 of beta, this is the first column of the matrix A. And similarly, the second column of the matrix B1 is A1 to A2 to AK2, but the second column of the matrix BA, it's equal to this coordinate vector. And similarly, we have done the remaining. Now we will evaluate the images of the vectors in the basis beta 2 under the linear transformation TW2. Now, TW2 of Vk plus 1 relative to the basis beta 2. Now this can be written as Now here we had written it a1k up to akk. Now this is equal to, this is a k plus 1, k plus 1. Now this is scalar, and vk plus 1, but not, because actually this is an element of the vector space W2, because again W2 is T invariant, so this restriction TW2 is a mapping from W2 into W2. So therefore this element is an element of W2, so we can express it as a linear combination in the basis beta 2. So we have this as scalar, vk plus, then vk plus 1 is a first vector in the coordinate in the basis beta 2, then plus, then we have a k plus 2, k plus 1. So this is the position. This k plus 1 represents the column number for this a, and this represents the second coordinate, second index of this scalar a. Then here we have vk plus 2 and so on. Then we have a n k plus 1 vn. But now this can also be written as, this is same as a k plus 1, k plus 1, vk plus 1, then plus a k plus 2, k plus 1, vk plus 2, then plus so on an k plus 1, then vn, then plus, in fact we could have written it, first we will write that 0, or we will write it now here. This actually equal to 0 times v1 plus 0 times v2 plus so on plus 0 times vk, then plus ak plus 1 k plus 1 vk plus 1, ak plus 2 k plus 1 vk plus 2, and so on up to an k plus 1 vn. But now this is the representation of TW2 of vk plus 1 in the basis beta. So this is T of vk plus 1 relative to the basis beta. Now similarly, T of TW2 of vk plus 2. Now this is again equal to a k plus 1 k plus 2 vk plus 1 plus a k plus 2 k plus 2 vk plus 2, then plus so on a n k plus 2 vn. But now this is same as 0 times v1 plus so on 0 times vk plus ak plus 1 k plus 2 vk plus 1.
It's 8 o'clock.
Then plus so on a n k plus 2 vn. And similarly, TW2 of vn relative to the basis beta. So this again with respect to the basis beta, but now this is equal to T of vk plus 2. So this is also the coordinate vector of T of vk plus 2 relative to the basis beta. So therefore here this last vector vn, TW2 of vn related to the basis beta, can similarly be written in this form. So this is equal to, this can be written as 0 v, or first we will write it as v1, this is a 1n vk plus 1, then plus a 2n vk plus 1, then plus so on a n vn. So this is vk plus 2 here. But now this can also be written as 0 times v1 plus so on 0 times vk plus a1n vk plus 1 plus a2n vk plus 2 plus so on a nn vn. But now this is the coordinate representation of t of vn relative to the basis beta. So therefore we have computed all the coordinate vectors related to the basis beta 1, beta 2 as well as beta. So now we can write the matrix. So thus the matrix A, this is an n cross n matrix. So this is an n cross n matrix. The first column is the coordinate vector of t w1 of v1. In fact, it is the coordinate vector of t of v1 related to the basis beta, and it is coefficients in the coordinate vector are a11, a21, ak1, then the remaining are 0. So therefore this is the first column. So it is a11, a21, so on, then ak1, then the remaining are equal to 0, 0, so on, 0. And similar the second column, it is the coordinate vector of t of v2 related to the basis beta. So it's a12 up to ak2, and the remaining elements are 0. So it is a12, a22 up to ak2, then 0, 0, 0. And similarly, so on. Now the coordinate vector of t of vk, then that has its coordinate as a1k, then a2k, so on, akk, then the remaining are all equal to 0. Now the next column is the coordinate vector of vk plus 1. Now we can see that the coordinate vector of vk plus 1 has first k coefficients equal to 0, and the remaining are in this way. So therefore we have this equal to 0, 0, so on, 0. Then here we have a k plus 1, k plus 1. Then here we have a k plus 2, k plus 1, and so on. This is a and k plus 1. Similarly, the coordinate vector of t of vk plus 2 has first k coordinates equal to 0, and the remaining are in this way. So therefore this column is 0, 0, so on, 0. Then here we have a k plus 1, k plus 2, a k plus 2, k plus 2, and so on, a and k plus 2. Similarly, the last column, it will have its first k coordinates equal to 0, 0, 0. And then here we have, this is a1n, a2n, and so on, a1n. Sorry, this should be equal to, we have written it wrongly, it should be ak plus 1n. So let us refine it, because it's in the k plus 1th column, k plus 1th row. So the coefficients may be written like this: ak plus 1 n, a k plus 2n, and similarly a n n. Now here this is, so therefore we can refine these also. So therefore here it is a k plus 1 n, then a k plus 2 n, and up to a n n. So this is A. So therefore this first one is A k plus 1n. A k plus 1n. This is k plus 2n and so on, and this is A and n. So therefore this is the matrix of, and this is the matrix A, which is the matrix of the linear operator T. But now we can clearly see this is the block diagonal matrix and this first diagonal. A11 to AKK, this is the matrix B1 in fact. So therefore we have this matrix B1. Now here we have a zero matrix, here we have a zero matrix, and this is the matrix B2. So therefore this completes the solution of this exercise. Now we shall come to a theorem. This theorem states that let T be a linear operator on V, be a linear operator on a finite dimensional vector space. Be a linear operator on a finite dimensional vector space V such that V is equal to the sum of its k T invariant subspaces W1 plus W2 plus Wk, where Wi is a T invariant subspace. Wi is a T invariant subspace of V for each I equal to 1, 2, up to k. Let Ci of x denote the characteristic polynomial denote the characteristic polynomial of T of Wi, sorry, this is Twi, which is the restriction of T from V to Wi. Suppose Ci of x denotes the characteristic polynomial of Twi, then the characteristic polynomial of T, then the characteristic polynomial of T is C of x, which is equal to C1 of x into C2 of x, so on, into Ck of x. So therefore this theorem helps us in obtaining the characteristic polynomial of a linear operator T in terms of the characteristic polynomial of its restrictions from V to these linear operators W1, V to these subspaces W1, W2, Wk, which are the T invariant subspaces, provided we have V as a finite dimensional vector space. Now let's do the proof of this theorem. So in the proof, we shall use induction. We use induction on K, that is the number of subspaces such that we can be written as the sum of these, direct sum of these subspaces. In fact, if we see this K is equal to 1, then the result is trivial. So therefore we assume the induction from k equal to 2. So the result is trivial. Result is trivial for k equal to 1, because then we will just get v is equal to w1 and we have nothing to do. So assume, so now let k be equal to 2. Let k is equal to 2. Then what we have? Then we have vector space V as a direct sum of its two subspaces W1 and W2. Then let beta 1, beta 2 be the basis of W1 and W2, and let beta is equal to beta 1 union beta 2 be the basis of V. Then by the previous exercise, then by previous exercise, then by previous exercise, we have the matrix of T with respect to the basis beta. This is equal to, this can be partitioned block diagonally as the matrix of TW1 relative to the basis beta 1, and then this next diagonal part is matrix of TW2 relative to the basis beta 2, and here we have a 0 matrix and a 0 matrix. So thus the result is true. Thus the result is true for k equal to 2. So assume, so now we shall assume the induction hypothesis. Let the result be true. Let the result be true for all vector spaces which can be written, or let us assume the result is true for, okay, for all vector spaces which can be written as direct sum of, which can be written as direct sum of at most k minus 1 subspaces which are T invariant. Which are T invariant. Then, and let's assume, and assume V is a direct sum of k T invariant subspaces W2 plus so on plus WK. Then we shall prove the result for this. Now let us define a subspace W, which is equal to W1 plus W2 plus so on plus WK minus 1. So therefore we have assumed a subspace W from V, which is a sum of k minus 1 subspaces, and these subspaces are chosen as W1, W2, WK minus 1 from this list, where this W1, W2, WK minus 1, they are in fact all the T invariant subspaces. So then it can clearly be seen that, so then since W1, W2, so on, WK minus 1 are T invariant. Since these are T invariant, thus that is that is T of Wi is contained in Wi for 1 less or equal to I less or equal to k minus 1 in fact. In fact, this is also true for k, but we just need it from 1 to k minus 1 for 1 less or equal to I less or equal to k minus 1. Now, since these are the T invariant subspaces, that we have this thing, so thus T of W, which is in fact, now this is in fact T of W1 so on W k minus 1, this in fact contained in T of W1 T of W2 plus so on plus T of W k minus 1. In fact, we should, it's actually the equality here. Now, but now this is equal to, this is actually coming from the fact that T is a linear operator, and from the definition of how we define this direct sum, because as we have this direct sum W1 plus up to Wk minus 1, that means every element of this vector space W is the sum of the vectors, one from W1, then second from W2, and the k minus 1 from Wk minus 1. And T is a linear operator, so this acts on this sum in this way. But now TW1, it is contained in W1. So this is now subset of W1 plus W2 plus so on plus Wk minus 1, which is equal to W. So therefore T of W is contained in W. So therefore W is also a T invariant subspace. So once we have W is a T invariant subspace, thus what we have, thus we have this V is equal to W plus Wk, where this W is the sum of first k minus 1 T invariant subspaces. But now we have expressed this V as sum of two T invariant subspaces. That is V is the direct sum of, that is V is a direct sum of two T invariant subspaces. Invariant subspaces. Thus, the result is true. Thus we have so actually what we needed to prove, here we have used this previous exercise. So then in fact we can see the characteristic polynomial is a product of characteristic polynomial of TW1 and the characteristic polynomial of TW2. So in fact we should add that here. So thus if this characteristic polynomial of TW1, so in fact we have actually written that in the definition. So therefore in this case, thus we have the characteristic polynomial of C of x, which is the characteristic polynomial of T. This is in this case true to be equal to C1 of x into C2 of x. So that the result is true for k equal to 2. So that is the result holds for t equal to k equal to 2. Okay. So thus we have this characteristic polynomial of x. So therefore this is equal to characteristic polynomial of t. This is equal to the characteristic polynomial of actually w into ck of x. where Ck of x denotes the characteristic polynomial of W of k, and Cw of x denotes the characteristic polynomial of W. Now, W is the sum of k minus 1 T invariant subspaces. Wk minus 1. So thus by induction, induction hypothesis, we have the characteristic polynomial of W. This is equal to the characteristic polynomial of W1 into the characteristic polynomial of W2, which is C2 of x, and so on, the characteristic polynomial of Wk minus 1, which is Ck minus 1 of x. So therefore, we have C of x. This is equal to now C1 of x into C2 of x into so on Ck minus 1 of x into Ck of x. So therefore we have showed that the characteristic polynomial of T is the product of the characteristic polynomials of the restrictions of the linear operator T on its T invariant subspaces, on its Kt invariant subspaces. So with this, we completed this proof.